So welcome everyone to the seminar today, and it will be our last seminar of this year. And our speaker today is Anatoly Dymarsky from University of Kentucky, and he will be telling us about his very recent interesting work connecting quantum codes and conformal field theories and holography. So over to Anatoly now.
Thank you very much. I greatly appreciate the opportunity to give a talk today. I will be speaking about a series of recent works I have been doing with a few collaborators. The topic is a new one. We are trying to find the role of quantum codes in the context of quantum field theories, and we found a very explicit connection between a family of particular quantum codes and specific particular conformal field theories in 2 dimensions, namely Narayan field theories. And here is an outline of my talk. I will first give you a quick overview of what the code is, assuming that not everyone knows what the code is. A part of it is completely intuitive, and then there is a beautiful mathematical theory of codes, and then there are a lot of open questions about codes. Despite mathematical simplicity, there are a lot of open questions about codes. And those questions, as I will show, they're very closely related to the open questions we have about conformal field theories. So first I will explain what codes are, and then also mention what quantum codes are. And then I will discuss how those codes are related to conformal field theories, especially of Narayan type. And once we make this connection tangible, we will see that open questions about codes basically mirror open questions about CFTs. And it seems like questions about CFTs are much more complicated. They're similar, but more complicated cousins. So the idea would be to start from the CFT and go to the code side and try to address those questions there. And as I said, these are still very, very complicated questions, those which mathematicians have been studying for decades, but they still seem to be simpler than the CFT questions. And basically, this is, if you think about it, as a big problem, as a program. That's a program of reformulating conformal bootstrap in some simple algebraic terms. So I will speak about that, the connection between codes and bootstrap, and also how codes can help us understand holography, especially in the context of this recently emerging idea that when you have holographic correspondence, on a gravity side, you have quasi-classical gravity, perhaps in a certain regime. But on the field theory side, you should not think about a particular boundary theory, but you should be thinking about a whole ensemble of theories. And in certain cases, we understand what that ensemble is very well. And this is a very specific context of GT gravity, where people understand what that ensemble is very well. There are instances where we sort of understand what the ensemble is. That's the instance of Narayan theories. And there are also instances where we have no clue what the ensemble is. For example, n equal 4 super Mills, which is dual to supergravity on a DS5 process 5. And we have no idea how to make sense of this correspondence by introducing an ensemble on the boundary side. So codes can help here because codes naturally come in an ensemble. There is not one code, but a whole family of codes of particular type. And by studying ensembles of codes, you can understand a little bit better what do you expect from the ensemble of CFTs. So that's the second direction where codes could be helpful. And then there are other directions which I will not be able to talk about today because this is work in progress. And that's more about understanding connection to holographic codes, those which are responsible for emergence of locality in the bulk, and also relation between codes and extended form symmetries. Okay, so let's start from the following intuitive slide. What is a code? A code is something which we use to encode, as simple as that. So this is something rather intuitive. Imagine you are talking with someone over the phone and the connection is very, very bad. And you want to say your name or something, and that person doesn't understand. Quite often in this situation, we resort to what is called phonetic alphabet. There's a particular phonetic alphabet used for military or whatever, but then you can invent your own. Each letter is substituted by a whole word. So if you want to say A, you say alpha. If you want to say B, you say bravo, and so on and so forth. So we most likely all of us have used this simple trick at least once in our life. So we understand very clearly what is going on here. But then intuitively, we never, maybe some people thought about that deeply, but most of us never thought about this very deeply. But intuitively, it's very clear that if you try to substitute a letter by the whole word, then you should choose words which are quite distinct from each other. If you have in your alphabet words which sound very similar, I don't know, something like November and December, you instead of saying N, you say November. Instead of saying D, you say December. But November and December sound sufficiently similar to each other, such that if the connection line is bad, someone can understand and hear November instead of December and vice versa. So intuitively, you understand that for the code to be good, to be of good quality, you need to choose words which sound distinctively. Alpha cannot be mixed with Charlie. Whatever you do, alpha, unless you completely shut down the connection, alpha cannot be mixed with Charlie. So that's the idea. So starting from this very intuitive idea, let's try to formalize it mathematically. So to formalize it mathematically, we'll consider what is called binary codes. So binary code is when instead of a letter of English language, so instead of Alpha, Bravo, Charlie, instead of a whole word consisting of English language, you will be using binary strings. And again, we have an example of a binary code called the Morse code. That's the code people use to connect, to transmit information between ships in the sea and other things. So you know that there are two signals, short and long, 0 and 1. So every single letter in the alphabet should be mapped to a word. It's called the code word. And the code word is a binary string of particular length. In case of the Morse code, different code words have different lengths, but this is inconvenient. So let's play the following game. Let's say that we have a binary code when we have capital K code words, and each code word will correspond to a letter in your original alphabet, which you try to transmit. And then each binary string has exactly the same, excuse me, I have a mouse here and I understand it's not connected. So each binary string has exactly the same length n. So your code words are binary strings of length n. And you have a lot of them, well, you have sort of a number of them, and you want the code to be good, which means that you want those binary strings to be distinctive as possible from each other. How to formalize this notion that two binary strings are different? You can introduce the notion of distance between binary strings by simply saying I have two binary strings, C and C prime. C is a code word, C prime is another code word. And the distance between them is the number of bits you need to flip, the number of bits of one code word you need to flip to turn it into another code word. It's very, very clear that the maximal distance is n. If you flip all n bits, you are able to get to any other code word starting from a given one. Well, if you flip at most n bits, you can get any code word starting from the given one. So this distance called Hamming distance. And basically, the code is characterized by the minimal distance between any pair of code words. The shorter that distance is, the worse your code is, because there is a possibility that you will have two sufficiently similar code words, and while transmitting them, one will be corrupted and will turn into another. Okay, so mathematically, you can illustrate the situation as follows. each code word is a binary string of length n, so it consists of zeros and ones. And you can interpret this code word, you can consider, you can interpret this code word as a vector of coordinates in an n-dimensional space. And since you only have zeros and ones, it means that each vector like that will parameterize a vertex on a unit cube. So let's consider a situation where you have two code words, 0, 0, 0, and 1, 1, 1. It means we have 2 points in a 3-dimensional space sitting at the vertices of a unit cube. In this case, this is this point and this point. Okay, and in fact, this code I have is a linear code. Linear code means that those code words form a vector space. If you start adding them to each other, mod 2, you need to do algebra mod 2. If you start adding them to each other, you will not generate any new code word. So imagine taking C0 and adding C1, you have C1, you have C1 and you add it to C1, you have again C0 because everything is done mod 2. So this simple example with those two code words is an example of 3, 1, 3 code. Now I need to introduce slightly different notations here. Notations n, small k, d, where n is the length of the string. Number of code words, capital K, is equal to 2 to the small k. In this case, small k is 1, so capital K is 2. I have 2 code words. And d equal 3 is the minimal distance, between any 2 code words. I have only 2 code words, and the minimal distance between them is 3. So this minimal distance corresponds to the minimal distance an ant needs to walk between those 2 vertices. An ant is only walking along the edges, and there are 3 edges the ants need to walk along. Okay, so this is a simple example. Is this clear? So let's go forward and develop some mathematical theory of codes. So here I introduced a linear code, which means that it's a vector space. But unlike conventional vector spaces where you multiply vectors by real numbers, or you multiply vectors by complex numbers, here we agreed that we will only multiply vectors by zeros or ones. So all algebra is done mod 2. Since it's a vector space, the total number of code words will be a power of 2. And then because of the linearity, if you try to understand the distance between any pair of code words, and there is n multiplied by, there is k multiplied by k minus 1 divided by 2 pairs of code words. If the code is linear, apparently you don't need to go through all possible pairs. You can choose one vector to be the origin. An origin is always an element in the vector space, so trivial code word is always there, and calculate the distance from the origin to all other code words. So the quality of the code, the weakest link of the code, is the code word which comes closest to the origin. So if you try to design a good code, your job is the following. You need to start with an n-dimensional cube. You need to start picking certain vertices in a unit cube. And your job, if you want to do a linear code, it means that those vertices should form a vector space, which means that the origin will be always there. And your job is to try to stick as many vertices, or to pick as many vertices as you can, while keeping the distance between them as large as possible. You clearly see that there is a contradiction here, there is a tension. More points on the cube you choose, less distance between them becomes. So it seems to be an optimization problem, and it is an optimization problem. How many points you can choose while keeping the distance large. But of course, also very complicated problem is to, once you decided how many vertices you will choose, how you will distribute them on the cube such that the distance between them will remain very, very large. And there are no known way how to solve this optimization problem. You can do different bounds. For example, you say, here is my first one, I choose second one at certain distance, then I have a sphere starting from here, a sphere starting from here, and the third one should be outside of those two spheres, not to come close to those first two. Then you put spheres around those three and put one outside these three spheres. That's how you do a bound, which is called Gilbert-Vershamov bound, a famous bound. So you can do bounds of that kind. But how you can actually design an optimal code which extremizes those distances, nobody knows. That's an unsolved problem. And even code capacity, when you have n dimension of your space going to be very, very large, and let's say you keep a ratio of k divided by n fixed, and you ask what's the best d, there are bounds, but we don't know what's the best d is. So basically, despite mathematical simplicity of the problem, you just have a unit cube and you start picking vertices, trying to maximize the distance between them. We don't know the answer, neither constructively nor implicitly. We don't know how well that job can be done. The solution to this optimization problem is not known. Okay, the code is parameterized, or I should say the code is characterized by its spectrum. It's a characterization in a sense that it doesn't uniquely specify the code, but it's a property of a code. The spectrum is the information about distances between code words and the origin. Okay, so let's assume you have a linear code, which means that you have an origin, that's a code word, and you have all other code words around, and you simply try to keep information about the distance from the origin to all of those other points. You don't want to keep the information how in space they're located. So most of information about code is lost, but the simple information, the spectrum, is the information about the distance from the origin to those code words. So this information can be packaged in the form of a polynomial. In the form of the polynomial. At first, this sounds like a ridiculous idea because the spectrum is simply the information about distances. So you can do the following. You can say, since everything is sitting on a cube, the distance from the origin to other points could be either 1, well, could be 0, that's the origin itself, could be 1 or 2 or 3 or 4 or 5. So I have all possible integer numbers up to n. The maximal distance on a unit cube of dimension n between any two points, it's an opposite points, it's equal to n. So why not take all of those numbers from 1 to n distances and simply keep information about how many points are located distance d from the origin. That's all. So you can keep this information. That will be a vector of integer numbers. But mathematicians say that we should use this vector of integer numbers to form a polynomial. They introduce a homogeneous polynomial of two completely auxiliary variables x and y. Since it's homogeneous, it actually means it's only a polynomial of one variable. And the coefficient of that polynomial, you have polynomial of integer powers. You have, let's say, y to certain distance d. The coefficient of that power in front of that power is literally the number of vectors located distance d away from the origin. So mathematicians say that this vector of integer numbers should be packaged as a polynomial. Mathematically, it's all possible. We know very well that polynomials form a vector space. So polynomials are, of course, characterized by their coefficients, which form a vector. But it's not clear at this point why this is such a good idea. But this is apparently such a good idea because if your code satisfies additional properties, what is called self-duality or other properties, then this polynomial will satisfy certain algebraic identities. So it's a good idea because polynomial naturally can, through algebraic properties, remember that the code was a special one, that the code satisfies certain additional properties. Okay, so that's all I wanted to say about linear codes and their mathematical theory, if you wish. Unless you have any questions at this point, let me try to go and speak about quantum codes. So quantum codes superficially is something completely different. Quantum code is an attempt to safeguard quantum information. You have a quantum state, and because of noise, it will be corrupted. and you want to find a way to preserve it. So at the level of the task that you want to preserve information sounds very similar to the codes, but since it's quantum mechanics, it all sounds very different. And to think about quantum codes, I suggest we do the following. We imagine this crazy situation that you design a perfect quantum computer. This laptop is a perfect quantum computer, and it has state psi L. L means logical. It's a state of a quantum computer. Then you have a bunch of auxiliary qubits, which are originally in the up state. But those qubits, they're unentangled. You simply have two different physical systems. You have an ideal quantum computer, then you have a microwave. And those qubits are inside the microwave. They're completely auxiliary, but microwave will start heating those qubits randomly. And after some time, they will decohere, and those qubits will become something like that. Let's say you're a purist. And of course, since you have no physical connection between microwave and quantum computer, your state of a quantum computer remained intact. So you don't need any error correction because physically speaking, no error was introduced. But say you're a purist and you say, no. I actually want to consider my microwave and the quantum computer as a whole physical system. And laws of quantum mechanics allow you to do that. And then this is your state. It's an unentangled state of a quantum computer and some corrupted qubits. And you're a purist, and you want, before doing something with your with your logical state, you want to bring those corrupted qubits back to the original state. How do you do that? Well, that's elementary. You measure those qubits, and unless they're in the up position, you simply rotate them in the up position. So what you do, you measure sigma z, that's a syndrome measurement. And if your qubit is not in the position you want it to be, you apply sigma x to rotate it to the up position, and that's the recovery channel. Okay, so that's completely trivial. When it becomes non-trivial is when you say, you know what, this of course was stupid. I had no connection between physical quantum computer and the microwave, but now imagine this is a logical quantum computer, and this is a part of the whole thing which you would call quantum computer. And then you will do a large unitary transformation, mixing those two things in the Hilbert space, in the full Hilbert space. Mathematically, it means the following. When you have the syndrome measurements, there will still be syndrome measurements, sigma z in a particular basis, but now you rotated that basis. And this, in your computational basis, that becomes a very complicated operator. So mathematically, a stabilizer quantum error correcting code is a situation when you have generators, GI, which in disguise as simply Pauli matrices in a certain basis. But in your physical computational basis of physical qubits, this is something rather complicated. But since in disguise, this is simply Pauli matrices, they have to commute, not only Pauli matrices, sigma z Pauli matrices, they have to commute, they have to square to 1, and the code subspace can be understood as a space stabilized by these generators. It's invariant under the generators, and since it is invariant under these generators, this is called the stabilizer code, and the corresponding group is called the stabilizer group. Now, if you're working on the conventional up and down basis, if you assume that your physical quantum computer, which includes the logical part, which includes this logical part and this part, your physical computer includes both of them. If it's made out of spins, which you can measure, so you introduce the conventional computational basis, you demand that your stabilizers in the computational basis look like an entangled product of Pauli matrices, sigma x and sigma y, or sigma x and sigma z. And then using sigma x and sigma z, you can make sigma y out of them. So this is your ansatz, if you wish. And this ansatz is dictated by your desire to be able to implement stabilizers on a physical platform where simple unentangled measurements on individual qubits are possible, but more complicated measurements are more costly and less possible. So this is sort of an input coming from your hardware. But then mathematically, to parameterize any product of Pauli matrices like that, we need a vector alpha and we need a vector beta. And vectors alpha and beta will be binary vectors. And basically, it means that every single generator can be understood as a binary vector of length 2n. And then it's very easy to see that if you start multiplying those generators, then essentially it will be an abelian group with respect to summing those binary strings. So of course, I'm skipping a lot of details, but the punchline is the following. Quantum codes, special quantum codes of the stabilizer type, can be reformulated as classical linear binary codes with some additional structure. The core of that is that this is a linear binary code of a length 2n. And then there's some additional structure because, well, for example, this would come simply from commutativity C1 plus C2 is equal to C2 plus C1. This simply will come from the fact that we are working mod 2. But then there are additional structures, for example, self-duality or self-orthogonality. This is coming from the fact if you want to have non-trivial solutions to these equations, then as a linear space over mod 2, then this quantum code should have certain self-orthogonality or self-duality properties. And I will not try to derive that. I just simply postulate that as a linear code, it must have additional structure. Okay, so how all of this is related to conformal field theories? At this point, there is no connection altogether. And unfortunately, we don't see a connection to a conformal field theory of a general type. But there is a very special conformal field theory, a family of very special conformal field theories of Narayan type, which are essentially free field theories. You have a sigma model where your fields are living on an n-dimensional torus, and you have a metric specifying n-dimensional torus, and you have a B field on the n-dimensional torus, and that's all you have. And since everything is living on the torus, you have certain periodicities, which means that your operators, vertex operators in the CFT are exponents of free fields, but those momenta, left and right moving momenta, they have to quantize in a particular way. And again, if you ever saw this, and this is discussed in Polchinski textbook in the context of string theory, toroidal compactifications, if you ever saw this, then of course this is a completely trivial thing. If you're seeing this for the first time, that might be coming just out of nowhere. So I will want to give you a simple analogy, a simple similar example. An analogy would be to consider a quantum mechanical problem, a particle moving on a circle. When a particle moving on a circle, you can say that your wave function psi x is instead defined on a line, but has to satisfy a certain periodicity or quasi-periodicity. So a particle moving on a circle is mathematically equivalent to a particle moving in a crystal. And then we all very well know that there is a Brillouin zone and a quasi-momentum, and the quasi-momentum has to be quantized, and the wave function could be only a linear superposition of exponents, because exponents, this is a Fourier theory, exponents form the full basis of periodic functions. So whether you're a mathematician familiar with a Fourier theory or a physicist who thought about an electron moving in a crystal, we understand very well that you will have an exponents and momentum will quantize. And if you think a little bit about it, the momentum will be living on a dual lattice, right? If you have, if you allow a twist, then you will have the whole zone, what we call a band. But if you are simply impose periodicity conditions that your wave function is strictly periodic, then the momentum k is living on a dual lattice. You have an original lattice in the physical space, and then you have a dual lattice of momentum. And in case of CFTs, you have exactly the same. You have a particle or a string in this case living on a torus, and then dual momenta quantize. And what kind of lattice you have as a result? As a result, you have what is called Narayan lattice. It's a self-dual lattice, and it is even, and it lives in the space with the Lorentzian signature. You have R to n comma n, so you have exactly the same number of plus and minus directions. This is not space-time. This is not space-time geometry. This is a target space geometry, and you have n positive directions and you have n negative directions. I am skipping what self-dual lattice is. If you have any questions about that, I can comment on this. But if you, of course, read Wilczynski textbook, then of course you know what I'm talking about. What is a lattice? I'm talking about lattices as if everyone knows what it is, and I assume that most people know what they are. But let me introduce lattices mathematically. Lattice is simply a linear space of vectors when you allow only integer valued coefficients. You have n vectors which live in n-dimensional space, so those vectors form a basis. And you only, if you only allow arbitrary coefficients, then you span the whole vector space. But you only allow integer valued coefficients. And as a result, you have a grid. For example, here on this picture, I have two basis vectors, v1 and v2. And clearly, if I only allow their linear combinations with integer coefficients, I will have a grid which is shown on the picture here. So that's a lattice. Okay. Now, a lattice is characterized, not parameterized, not uniquely parameterized, but is characterized by the spectrum. What is the spectrum? The spectrum is a very, very simple thing, and it should resonate with the definition of the spectrum we introduced for codes. A spectrum of the lattice is simply the information about distances between all lattice vectors to the origin. If you have a lattice of a particular kind, let's call it even lattice, it means that the length squared of any vector, let's say you have this vector, length squared of any vector is an even number. That's what is called even lattice. And if it's an even number, you have all possible even numbers, 0, 2, 4, 6. You want to keep information how many vectors you have located that distance away from the origin. That information would be an infinite string of integer numbers. For example, distance 0 away from the origin, you have only one vector origin. Distance 2 from the origin, when I say distance, I mean length squared. You have certain number of vectors. Distance 4, you have certain number of vectors. You have an infinite string of integers. That's called a spectrum. Why we care about the spectrum? Well, because information about the spectrum can be packaged in form of the theta series of a lattice. And theta series is literally mathematically only the vehicle which retains information about the spectrum. You go through all lattice points, you calculate the distance from the origin, and then basically you introduce auxiliary variable tau, and you have a generating function which remembers the only information it remembers the distance from the origin. But if you're a little bit familiar with Narayan theory or mathematics which appears in the context of two-dimensional CFTs, then you immediately recognize those theta series as something very, very important. Because for special Narayan lattices, they will become, or for special chiral lattices, even self-dual lattices, this will become modular forms. They will have very nice properties on the modular transformations of the modular parameter. So in the context of modular theory, those functions are very, very important. Of course, a simple version of this function could be Jacobi theta series themselves. For example, theta 3, Jacobi theta 3 is something like q to the power n squared, and q is e2 pi I. So it's very, very easy to see that this Jacobi theta function, theta 3, is simply a theta series for a one-dimensional lattice like this. Okay. Now, an interesting thing is that codes, at least many different types of codes, linear codes, can be naturally related to lattices. Let's see how much time I have. Okay. Codes can be very naturally related to lattices. And the construction is the following. It's called construction A. There are other constructions, but this is the simplest possible construction. It says the following. Remember, the code was a number of points on a unit cube. For simplicity, I'm drawing here a unit two-dimensional cube, and it is shown in orange. It's a unit cube. This is my origin. This is my origin. This is my point 1, 1. Okay. I have a unit cube, and that's my code. To build the lattice, let's take this unit cube and move in all directions, up, down, in all directions in a parallel fashion with a step 2. If I do it with a step 2, you will easily see that this is another, and this is another, and this is another, and then this is another, and this is another. I'm moving in all possible directions with a step 2. Okay, and if you just forget about what I have drawn now, and I will remove what I have drawn now, you will recognize once again that you have a periodic structure which is mathematically a lattice. So that's what is called construction A. You start from a code and you build a lattice. You can say, oh, it's a stupid lattice. It's a sublattice of a cubic lattice, because obviously the grid here is cubic. So yes, I have something like a sublattice of a cubic lattice, but my lattice is not a cubic lattice. It's an interesting one. It's this one. My lattice is actually not a cubic lattice. It's sublattice of a cubic lattice, but this is something non-trivial. And I obtained it directly from the code. So you see that I can obtain something rather non-trivial. I cannot claim that I can obtain everything possible, every possible lattice in the world, but a rich class of lattices can obtain this way. And the very nice thing is the following. If you obtain a lattice from a code, you want to ask, what's the spectrum? Or in other words, what's the theta series? Then there is actually a very, very easy way to calculate it. You take this polynomial. I didn't introduce the name. The name of this polynomial was Enumerator Polynomial. Let me go back. This is a polynomial we introduced when we were trying to keep track of the spectrum of the code. It's just an auxiliary polynomial of dimension n. That's it. And for example, for the code, excuse me, for this code, I think enumerator polynomial will be something like x plus y. That's it. Just two code words, so you will have x plus y. Something very, very simple. But the idea is the following. If you build a lattice starting from the code, then the theta series will be given by a numerator polynomial with the auxiliary variable substituted by Jacobi theta series. Why this is the case? Well, to understand intuitively why this is the case is because of the following. Each point, you remember we had a point at the origin, and that point was moved with the step 2 everywhere. Each point of the code give rise to, I want to say a sublattice, but mathematically this is incorrect because these points might not form a lattice. So when I say sublattice, I will mean a subset in a lattice. It's not a lattice, it's a subset in a lattice. So each code word gives rise to a subset in a lattice, which looks like something cubic. And since it's something cubic, Jacobi theta series takes care of that. And another, let me change color, another code word gives rise to another subset, which is also cubic. So another theta series takes care of that. And if you start thinking about that and trying to calculate, you immediately come up with this formula. It's a very, very straightforward business of just sitting down and trying to calculate it. Okay, so now let's go back to Narayan theories. Narayan theories are based on Narayan lattices, and we can try to calculate their partition function. And of course, I'm appealing here to your prior knowledge of Narayan theories that you already know a little bit what it is. You calculate partition function and it becomes and it becomes the theta series of your Narayan lattice divided by Dedekind theta function. I have a completely ridiculous typo here. I do not know what I was thinking when I was writing this. That should be Q KL squared over 2, and then you have Q bar K right squared over 2. Somehow, instead of you see, I have a mess here. Instead of Q bar, I have something K, because sometimes P and K people use it interchangeably. So here I use K left and K right. So this is the theta series of a Narayan lattice. It depends on the modular parameter of the torus, but it's a non-chiral CFT, so it depends on Q and Q bar. So if I want to calculate a partition function of Narayan theory, I need to know how to calculate this theta series. And here comes the punchline. Here comes the punchline. I'm skipping all the details, but now I will combine everything together. If you consider quantum codes of a particular type, and quantum codes of particular type can be understood as linear binary codes with some additional structure. I'm sorry, with some additional structure, then those linear codes, linear binary codes, using construction A can be turned into a lattice. And this additional structure will actually guarantee that this lattice will be even self-dual in a space with the metric Rn, n. If you simply start with classical linear codes, you can promote it to be a lattice, but that lattice will not be even self-dual in this space. At best, it will be even self-dual in a space with Euclidean metric. Okay? That's the best you can do. But if you start with a quantum code with this additional structure, you will actually have a Lorentzian lattice. And that's what the step, non-trivial step we did in our paper. It was known for a while that classical codes can be mapped to Euclidean space through lattices. There is nothing new about it. And people, of course, knew that if you start with special classical codes, you will have Euclidean self-dual lattices, which are interesting in their own right, of course. There is this famous Leach lattice and E8 lattice. And if you look through Green-Schwarz-Witten or Polchinski textbook, you will see those lattices appearing. People study them in the context of string theory. But the non-trivial step was to recognize that if you start with quantum codes of a particular type, you will have a Lorentzian structure, and therefore you will have Narayan theories. And now if I want to calculate partition function of a Narayan theory, I need to calculate the theta series of the corresponding Narayan lattice. And that I can do simply by introducing a numerator polynomial of a quantum code. A numerator polynomial of quantum code will depend on more variables because it's a binary code of length twice the normal. Since you have twice the normal length, you have, instead of 2 variables, you have 2 by 2, you have 2 to the power 2, you have 4 variables. But in any case, it's just a polynomial of 4 variables. And once you take this polynomial of 4 variables, and instead of the variables stick in certain combinations of Jacobi theta functions, you obtain the partition function of a Narayan CFT. So that's basically the result. And now let's see how we can understand this result. The schematic picture is the following. You have a space of all 2-dimensional CFTs, which is a poorly understood space. That's a space we as a community are trying to understand. We're really trying to understand this with the conformal bootstrap and in the context of holographic correspondence connection to 3-dimensional gravity in EDS3. We really want to understand the space, but we don't have any mathematical way to describe it. It's just too complicated. Then you have a corner, which is a well-defined and rather well-understood corner, but not thoroughly understood, called Narayan CFTs. And in that space, which is a continuous space, you have a bunch of points, and with it, as central charge increases, the number of these points becomes exponentially large, which are CFTs associated with quantum codes. There are many points here that are not fully dense in this space. They are sitting somewhere in particular directions. How and where, I hesitate to tell you exactly, but I'm just trying to say that they might describe well certain parts of the space, and they might describe well certain properties of the space, because they're discrete points, but they form a cluster in a sense. So if you try to do certain averaging over this thing, and we will hopefully talk about that later in the talk, instead of averaging over the whole thing, you can try to average here. Of course, the result, the mean value, will be different, but the fact that you can average, and for example, you have self-averaging property, and self-averaging property means that if you randomly choose a point, it will characterize the whole space. It also will be true here. If you choose a point among those purple points, it will characterize the whole cluster. So self-averaging, and I will try to explain that later, is likely the property which code CFTs describe. Now let's speak a little bit more about conformal bootstrap. Conformal modular bootstrap. Modular properties is the property of a partition function to be invariant under those two transformations of the tau parameter. And so far, you describe your partition function in terms of the codes in a numerator polynomial. For invariance under this modular transformation boils down to simple algebraic identities at the level of a numerator polynomial. So this is a crucial thing which comes directly from here. The relation between CFTs and codes, if you wish, can be understood as an algebraic ansatz when I'm writing my partition function in terms of a polynomial and arguments of the polynomial of specific combinations of Jacobi theta functions. And if I write this ansatz, then I reduce modular invariance, which is a complicated thing. I reduce it to simple algebraic identities. And now if you try to do modular bootstrap, which means that you try to constrain possible possible values of Z based on modular invariance, you can try to reduce that to the space of polynomials. You say, I'm only interested in polynomials which satisfy those two identities, and also certain positivity of coefficients, which in turn will become positivity of coefficients of partition function. So if you do that, you reduce a rather complicated problem with modular bootstrap to a much more simple problem of doing constraints at the space of polynomials. You can ask, what is this game of doing constraints in the space of polynomials? Is it a new game? No, it's not a new game. It has been known in mathematics for decades. Basically, mathematicians were doing modular bootstrap for decades at the level of polynomials, and this is called the Sartre linear programming constraints. So they're trying to constrain what is the best code you can write by starting with a polynomial and imposing constraints like that. Surprisingly, despite the fact that you're just dealing with the linear algebra, linear algebra, yes, but you're just dealing with the polynomials and linear programming in the space of polynomials, something superiorly simpler, vastly simpler than modular bootstrap. Even in the space of polynomials, exact answers are not known. So basically, what codes allow you, if you're theorist or practitioner of modular bootstrap, what codes allow you to reformulate the problem in simpler terms and try your luck there. And I think this is a valuable exercise, because once we understand this space of polynomials better, then you can learn those lessons and try to go back to modular full space of two-dimensional CFTs.
Anatoly, can I ask something?
Yes.
Here, So why were they, so this is equivalent to some SL to Z, this at the level of polynomials. So what was the motivation to look into such transformations?
These transformations?
Yeah, from just from the point of view of, say, the polynomials, or from the point of view of the original codes.
Right. So there are different properties the original codes satisfy, and these are exactly the codes which translate into nice properties of the lattices. So if you, let's speak about chiral case. We want to have a modular form. To have a modular form, you want the theta series to be a modular form. For that, the lattice must be even and self-dual. Okay, that is known. If it is even, then it means that partition for a theta series would be nicely changing under this. And if it is self-dual, then it will be nicely changing with respect to this. You can ask, what is the property of code I need for the lattice to be even and self-dual? Well, self-duality of a lattice becomes self-duality of a code, and evenness of the lattice becomes what is called double evenness of a code. Forget about double, some evenness of a code. So you have certain properties of a code, which is an algebraic property of a code, and you can ask how it is reflected in the enumerator polynomial. And the answer is, it is reflected in this way through algebraic identities.
Yeah, so basically that was what I was asking. So there's a code equivalence of the SL to Z property. Is there some code?
Yes. You sometimes it's at the level of codes. It's a priori not clear what tau is and why these two properties are important. There are other competing properties you can choose, but once you go to the lattice, you can pick and you can understand what you want and go back and pick and choose the properties of the code you need, and they will specify those to algebraic identities.
Just another question here. So would different codes give rise to different partition functions? Or is it like, or is there one-to-one?
Normally, that's what is discussed later in the talk. Normally, different codes will give you different polynomials. But my next question is, can I use this connection to get some interesting mileage, some concrete results, not theory, some concrete results? Apparently, codes are not parameterized uniquely by polynomials. The situation is complicated. Different codes might have the same polynomial. And there might be a polynomial which satisfies all identities, but there could be no code for it. That makes the situation interesting because people were looking in the following question a long time ago. Can one hear the shape of a drum? Similarly unrelated question. Can one hear a shape of a drum? Can you recognize the geometry of a space from the spectrum of the Laplacian? And apparently the answer is no. The answer is no, because people were considering Laplacians on tori, and Laplacians on tori mathematically is the same as the spectrum of a lattice, because a lattice is a periodic structure, which is basically a bunch of tori stuck on top of each other. So if you want to study Laplacian on a torus, it means that you want to study theta series on a dual lattice. And people were studying theta series on lattices, and they recognize there are different lattices with exactly the same spectrum. And this is a famous example by Milner that in 16 dimensions, E8 plus E8 has exactly the same spectrum as D16 plus, but these are two different lattices. And we have duality between two different compactifications of string theory, which utilize this mathematical result. We have a string duality which utilizes this mathematical result. Apparently, you can have something like that in the case of Narayan CFTs. You can choose different codes, quantum codes, with exactly the same spectrum. For that, you need to go for n equals 7 or larger. So you need to have 7 dimensions or larger. But you have pairs of quantum codes, which are different codes, but they have exactly the same spectrum. The resulting lattices are different lattices with exactly the same spectrum. Resulting CFTs are different CFTs with exactly the same partition function. So we identify this explicitly. When you have central charge 7, you have a unique pair. When you have central charge 8, you have over 60 pairs and triples. When you go to central charge 11, there are thousands of pairs, triples, tuples, up to 11 tuples. There is no obvious structure. It's just there are many of them. That is interesting because if you're a practitioner of modular bootstrap and you identified a solution numerically, you cannot jump to a conclusion what kind of CFT you're dealing with, because there are explicit examples of CFTs with the same partition function, but CFTs are distinct. So this is one thing. And second thing, there are also fake partition functions. They're very, very explicit polynomials. They're written in our paper. There are no codes associated to them. You can build Z. Z will satisfy all the properties partition functions should satisfy, all the positivities, all the modular invariants, but there is no obvious CFT associated to it. And now we are very close with a graduate student from Weizmann, Rahit Kalur, and Ofer Aharoni. We're very, very close to proving that those partition functions are completely fake in the sense that there is no CFT for which this Z is a partition function. So this is another explicit result which comes immediately once you start thinking about codes. In the third application, you say, okay, the usual game I play in the modular bootstrap is the following. I fix my central charge and I try to maximize my spectral gap. People play this game a lot because they hope to be able to go to large central charge, and once they maximize spectral gap, they hope that the result in CFT will be holographic. But for small spectral gap, can you do it? People did it numerically with good success, but then you can actually do it sort of using codes. And we have shown in our paper that for these values of spectral central charge, code theories, special codes give rise to CFTs with a maximal spectral gap. Unfortunately, we don't have an underlying theory in a sense that I cannot tell you right away that a code theory will be a theory with a maximal spectral gap. I have to prove it other ways. But at least it's clear that it's clear that this space of code theories is rich enough, and at least for certain values of central charge, the theory which maximizes spectral gap is one of those purple theories. Okay? And then more recently, this summer, this work was extended in a collaboration with Adar Sharon. We also consider central charges 6 and 7 and considered slightly different construction, generalization of our construction, different codes and different construction, and optimal theories, those which maximize spectral gap, are also coming from codes. And now we are trying to generalize that with my graduate students here in Kentucky and see if we can do that for other central charges, and ideally for all, but that's of course not something we will be able to prove. This is something maybe we will be able to conjecture. But now we want to do other central charges. 3, 4, 5, 6, and 7 are covered. In some way, 1 and 2 are trivial, but we want to do 8, maybe 9, and then try to see if we can maybe speculate about other larger values of central charge. I'm done about my first part. Yeah, there's also connection to homogeneous. You can ask, wait, I only discussed torus partition function. If there is a continuation to the story, if I want to consider homogeneous, yes, there is a continuation of the story. And my graduate student, together with collaborators, they did this nice independent work, which I hope will appear on arXiv soon. They considered homogeneous partition functions, and it is also related to codes. And in this case, enumerator polynomial have to be generalized. Mathematicians already invented that some time ago. It's not a very famous topic in the mathematical literature, but people did this work. enumerator polynomial can be extended in the following sense. Conventional numerator polynomial is a sum over code words. And if you want to do genius 2, you need to have a sum over pairs of code words. And for genius 3, you would need to have a sum over triples of code words and so on and so forth. Okay, so I'm basically done about the first part, and I assume that my time is up. So shall I maybe jump to conclusions?
Well, you can, I mean, we usually go a little over time. So if you want to take 10 more minutes, please.
Okay, I'll take 5 more minutes. Thank you. Thank you. There is another part to the story, how codes could be helpful. And this is in the context of understanding holographic correspondence, this new version of holographic correspondence, which is hypothetical, which we don't understand, where you try to assign to a gravity in the bulk, you try to assign an ensemble of theories. And if you want the gravity to be quasi-classical, semi-classical, you immediately see that in a quasi-classical theory, in a classical theory, there is no uncertainty or ambiguity. All observables have specific value. There is no variance to that value. It's not quantum mechanics. How can you describe that on the boundary side? On the boundary side, you have an ensemble of theories. Yet alone those quantum theories, so there will be quantum uncertainty, forget about that, but there is an ensemble of theories. What kind of answer you can get from an ensemble? You will have variance. So to reconcile that, it's not difficult to reconcile. This is the same reconciliation we have in the context of statistical physics. You have statistical physics, you have thermal ensemble, that would be a microcanonical ensemble or Gibbs ensemble. But when you do classical measurements, you have answers with certainty, temperature or pressure, there is no ambiguity. Why? Because you're speaking about certain quantities, macroscopic quantities, but more importantly, those quantities have the notion of self-averaging. If you consider this quantity, if you evaluate this quantity in pretty much any representative from your ensemble, you take any representative from your ensemble and you calculate the value of that quantity, the answer will be exactly the same with an exponentially small precision. In other words, there is variance associated to an ensemble, but it is negligibly exponentially small. This is called self-averaging. And in the context of statistical mechanics, we take it for granted. In the context of quantum physics, especially in the context of experiments, which people do now, this is more of a topic and people discuss it, but this is something rather well understood as a mathematical concept. I'm just trying to say it's sort of a trivial thought. It's not the thought which people have discussed in the literature a lot, but this is a trivial thought. If you hope to describe something quasi-classical in the bulk, your ensemble has to have self-averaging properties. So we were trying to understand how that will work in the case of Narayan theories. But the case of Narayan theories is mathematically more involved. So I want to have certain model, a playground. Well, first of all, if you go with this route of self-averaging, you can make really a stronger conjecture, which goes beyond self-averaging. And you can introduce the following scenario. You will say, wait, I have an ensemble of Narayan theories, and they're dual to something people call U1 gravity. But what if I have a unique Narayan theory? How should I think about that? A scenario inspired by thinking about quasi-classical gravity in ADS3, but conventional gravity with the Riemann tensor and everything. A scenario which, in the conventional case of a conventional gravity, you can have weakly coupled limit, something you might not have in the U1 gravity. But the scenario is the following. An individual Narayan theory will be described by U1 gravity plus some additional particles, some additional states. If you have weakly coupled limit, something which we do not have for Narayan theory, that's why it's a conjecture, and this is not an enormously solid conjecture. If you would have weakly coupled limit, then you would say, I must have all the states of my U1 gravity plus perhaps some additional states. And that means that the density of states, excuse me, I'm again using my mouse, I should be using my stylus, that the density of states of any given Narayan theory cannot plunge below density of states of gravity. So this is gravity, and this is the same as logarithm rho bar averaged over all theories, over all Narayan theories. So this is a ridiculous conjecture from the mathematical point of view. This is a ridiculous conjecture from the mathematical point of view, because what I have written here is a mathematical nonsense. I'm saying you have a set. You average something over that set. Now I want all elements in this set to be at least as large as the average value. But how on earth is this possible? If you have a set and you average something over the set, then it's clear that the mean value is smaller than the half and larger than the other half. It's ridiculous to demand that all values will be larger than the mean. Why am I making this conjecture? I'm making this conjecture because of two things. I'm inspired by the picture of gravity being weakly coupled to additional states. That's a physical picture. But mathematically, to make sense of this conjecture, I'm saying I first need to consider infinite central charge, because that's the only limit where quasi-classical gravity may emerge. And I truly might hope to have any well-defined weakly coupled regime. And in this limit, variance associated with the corresponding ensemble will shrink to zero. So basically, by saying that the mean value is simultaneously the smallest value, I'm basically pushing forward the idea that the variance is vanishingly small. And in the limit of infinite central charge shrinks to zero. So this conjecture goes beyond self-averaging, but again, it is rooted mathematically, or at least it requires mathematically as a consistency check. It requires the statement that variance associated with the ensemble of CFTs will be vanishingly small.
So is it equivalent to saying some sparse spectrum at lower than
No, because we're not talking about conventional CFTs. We are talking about Narayan CFTs. And you can repeat the analysis of Hartman, Keller, and Stoika. And we repeated it in our paper. The reference will be on the next slide. And there is no you have a notion of sparseness. You have a notion of sparseness, which must be satisfied. But of course, this notion of sparseness, if you remember the work by Hartman, Keller, and Stoika, you have something like a curve associated with gravity, and you have certain curve coming from analysis of the modular invariance, and then this is roughly C over 6, and this is roughly C. Excuse me, this is roughly C over 12, and this is C over 6. Sparseness guarantees that this condition is satisfied for sufficiently large values. But it tells you nothing about this region, which Hartman called Hartman and collaborators called non-universal region. And they actually had examples that you can have different behavior in this region. And my question is the following, my scenario is the following. Can you have a sparse theory with a density of states like this? It will be, of course, larger than gravity at large values, but it will plunge below at intermediate values. And a simple analysis, or maybe, excuse me, let's even say like this. So if I do something like this, it means that my spectral gap here will be larger than C over 6. I know that this is a messy picture, and not everyone remembers very well what Hartman, Keller, and Stoika were saying. there is a reference to my paper with Al-Shapir where we discuss this very, very carefully for Narayan theories. But let me tell you something completely uncontroversial. We know in the context of conventional CFTs that there is mathematical proof that spectral gap cannot be larger than this. And now with the modular bootstrap, people even move it to something like this, right? But there is an expectation based on gravity that the maximal spectral gap actually should be like this. But that hasn't been proven. And unlikely we will be able to prove it easily. Certainly not the way, certainly Hartman, Keller, and Stoica squeezed everything they could out of their analysis. We cannot get C over 12 from there, right? So there is the non-universal regime where very close to the threshold of black hole microstates. And you cannot mathematically show that CFT must have those states. Spectral gap potentially could be larger. So what we are conjecturing here is that spectral gap in the Narayan case will not be larger. That the spectral gap will be exactly where your black hole tells you the spectral gap should be. So this is a conjecture. There is no way to prove it. But what I'm trying to say is that for consistency of this conjecture, we must have self-averaging. And in particular, we should have vanishing variance in the ensemble of Narayan theories. Okay, so maybe at the level of this statement, I hope this is uncontroversial. So the consistency check we did not consider Narayan theories because we knew that Maloney and Collier were working on this, and we didn't want to scoop or compete. There was no point to do that. We wanted to show, and additionally, we wanted to show that code theories could be a useful playground. We consider the ensemble of code theories, and we have shown that the variance is exponentially suppressed. And we also consider the Euclidean case and chiral CFTs, and also have shown that the variance is exponentially suppressed. And more later this summer, Maloney and Collier published their own paper, and they came exactly to the same conclusions, that the variance is exponentially suppressed, which means that the conjecture I have put forward in the previous slide might be correct, that the threshold of states might be simply determined by the black hole. But for me, in the context of this talk, what is important, this justifies using CFTs to study ensemble properties. It's very difficult to understand ensemble of all CFTs. Even the ensemble of all Narayan CFTs is mathematically non-trivial. But code theories give you a chance to understand, it's a discrete ensemble. They give you a chance to understand things a little bit better in a simple way. So I think that's the value of the code theories I want to emphasize. Here are my conclusions. We connected codes to CFTs, and that provides a new tool to study both individual theories and ensembles. For individual theories, there is obvious connection to modular bootstrap. In a sense, codes give you an algebraic ansatz to solve modular bootstrap. You can try to find optimal theories, and we found a few. Those, of course, which have been found previously, but now we will try to extend that to other values of central charge. So we'll try to find optimal theories. We found a lot of isospectral theories. We found fake partition functions. All of that has obvious relation to modular bootstrap. For example, with Z, you will be able to see it. If you want to do it, you will be able to see it through modular bootstrap, but bootstrap will never tell you it's a fake one. It's not associated with any CFT. So this immediately shows you that bootstrap has limiting potential. And then another thing we did with the codes, we studied ensemble properties. We have shown that the variance is exponentially small with a central charge. That is, of course, the picture you have intuitively because you think that in a large central charge limit, you will have something classical. But the codes give you a simple model where you can calculate that rather explicitly. There are a lot of physical questions remain. Really, what the meaning of code is. We have a nice algebraic relation to codes, but you want to know if there is any meaning in the context of quantum information, if there is any connection to holographic codes which are responsible to locality in the bulk, emergence of locality in the bulk. We see in the ongoing research certain connection between codes and higher form symmetries. All of these questions are very interesting and we are thinking about them and there is certain progress. But then there is even bigger question to go beyond Narayan theories. All of that is in the context of Narayan theories. There's a bigger question to go beyond Narayan theories and understand if an appropriate generalization of codes, which very, very likely will be infinite dimensional, there's some algebraic structure which will be an infinite dimensional structure, can be a counterpart of codes for general non-Narayan CFTs. That would be really a holy grail of all of this, because if we can have that, that will give you a new tool to study general two-dimensional CFTs, and maybe there will be a way to understand holographic correspondence and self-average and other properties in the more general case when you have gravity in the bulk. All right, with that, I would like to stop. Thank you very much.
Thanks for this great talk. Okay, so we should take questions now. There are questions. Yeah, please ask, Shiroman.
Yes. Can you just have you heard of this 5-qubit error correcting code that encodes 513?
Yeah.
I think.
Of course. Yeah, of course.
So what is the does the CFT correspond to that, or is there have any interesting properties?
No. No. So to have a CFT, we must have what is called self-dual codes, and from the so the quantum code, usually denoted like this, they have k logical qubits, and this is the number of physical qubits. But we are dealing with self-dual codes. We're dealing with self-dual codes. For self-dual codes, k is equal to 0. You are encoding no logical information.
So a quantum state.
A quantum state.
So just a quantum state.
I was saying quantum. I was calling them quantum codes. Quantum. Well, more accurately, it's called quantum error detection code. It's a code which cannot store information and correct it, but it's a code which can detect any error which has happened with your unique state, which is a code subspace in the Hilbert space.
So that 5-1 code is related to a 6-0 perfect tensor.
5-1 is related to 6. I think 1.
A 6. It's 5-1-3, but there's like a 6-0.
It's 3,
code
right? It's a t is equal to 1, right?
Yeah, it's like a perfect tensor. So there's a 6-0 code, which is, I think, I don't know what D is.
What is a perfect tensor? Sorry, I just forgot.
It's like an MDS code. Well, it's just the idea is you have an error correcting code and you take the output of it and you can sort of turn it into an input, and then it's just a state.
Right. Perfect tensor. Right. Perfect tensor is in the context of this unitary circuits. Right. So I will not be able to make an immediate connection with this perfect tensor. But if you're saying that this one can be related to 60 something, do you know what this something is? Is it maybe
whatever the largest value is?
It's a hexacode, and then it's a hexacode, right?
Yeah.
Okay, good. So hexacode gives rise to an Orion CFT with C equals 6. Is it a particularly interesting CFT? It has certain properties. It has largest spectral gap among all code CFTs, but not among all CFTs. But then there is a generalization of our construction, which I mentioned with Adar Sharon. And with this generalization of this construction, a hexacode actually is mapped to the optimal CFT with C equals 6, which has maximum possible spectral gap. So the hexacode, so this is literally the hexacode. This is 604, the maximal possible.
Here you said non-binary codes.
These are F4 codes, but F4 codes can be rewritten as binary codes.
Right.
Of length twice large.
Right. So you still mean qubit codes when you're saying that? Qubits, when you say non-binary.
Non-binary means
not classically
not
binary,
classical,
but quantum mechanically still it's a qubit.
Yeah. F4 something like that. Yes.
Yeah. So yeah, this. Okay, so that's nice.
Yeah. I'm not sure why I said non-binary. Maybe to emphasize that there's a non-chiral.
Well, classically, from a classical point of view, they're non-binary. Yeah.
Yeah. The right field is F4. You can write it as Z2 because F4 can be embedded as Z2 cross Z2. But yeah, I'm not saying anything interesting here.
Okay, yeah. So yeah, thanks a lot for the talk. It was very interesting.
Thank you.
Okay, any further question? Yeah, okay, so maybe I have a very silly question. So is there any obvious meaning to the code subspace in this context, in this class?
Right, so you're asking a very good question and a very important question. What's the physical meaning? What's the physical meaning of quantum information? Here's a cartoon. I want to say right away, this cartoon is wrong. It sounds very, very compelling, but it's completely wrong. Well, it's not completely wrong, but it's wrong. So you have, well, whatever, a torus. So you have a CFT, and then you have a quantum code, and you have n qubits. So you would have 2 to the n states. You will have 2 to the n states of those qubits. And within that space, you have one particular entangled state, which is your code subspace. You want to know how you can see all of that on a CFT side, or maybe even holographic side, because you can think of this as being a boundary of ADS3, right? So we were trying to see first if you can see 2 to the n states of those qubits. And we know that Orion CFT is dual to Chern-Simons. So you will have u to the 1 Chern-Simons, well, u to the 1 to the n Chern-Simons, and then there are states of Chern-Simons. And it's very, very well known that the wave function of Chern-Simons, path integral of Chern-Simons on a space with a boundary, can be understood as a wave function living just at the boundary. And it's very, very well known that this space is discrete, it's finite dimensional. And with some thinking, you can recognize that in certain cases, there will be exactly 2 to the n states, boundary states. And you can hope that combining them, you can have an entangled state. So this one, once I thought about that in the beginning of this project, I thought, oh, this is it. I will understand holography and quantum codes right away. And it is indeed very suggestive. I think it does sound interesting. But like that literally doesn't work. It doesn't work for many reasons. These are non-chiral theories. So besides psi, you have psi bar of a bar. And also direct counting doesn't work. You can start with a particular theory and we know the bulk dual to it. And you see that things don't quite work. I think a much better idea, more nuanced idea, is that those codes these are abelian theories in the end of the story. They appear in the context of defects. To see those finite dimensional Hilbert spaces, they might not appear as Hilbert spaces, but they might appear as finite dimensional structures, abelian groups. You need to introduce boundary defects on your CFT side, and then it will have certain additional symmetries under which those boundary defects are charged. And then you will see finite dimensional abelian groups, which can be associated with codes. And then, of course, that can be described holographically. But for that, you need boundary defects and higher form symmetries. So this is something I'm working on right now with Matt Buikan from Queen's Mary, and he has this wonderful graduate student, Raja Krishna. And we are making progress, but I'm not ready to tell you the full answer at this point.
Okay, wonderful. Sounds intriguing. Okay. Okay, so thanks for the great talk again, and thanks for your time, and thanks for everybody for attending it. And so, so hope to see you again back, and hope that you will visit us in Chennai at some point also, Anatoly.
Would love to. Yes. Thank you.
Okay, so have a goodbye to all then, and have a great day, and see you in the next year. Have a very good, happy new year.
Bye-bye.
Bye.